Let us see tertiary winding or three winding transformer. So in addition to primary and secondary winding, it has third winding also. In addition to primary and secondary winding, this transformer has third winding. Right. So we have this primary winding with supply voltage, number of turns say N1, secondary winding, connected to load, with N2 turns, and tertiary winding is also there, which can be available for different voltage to any type of load N3. Right. Current here will be I2, I3, and this is I1. Voltage per turn will be same for all windings. So V1 by N1 equal to V2 by N2 equal to V3 by N3. Total kVA seen from primary and secondary will be same. So kVA S1 equal to kVA of this secondary winding and plus kVA of tertiary winding, that is third winding. This is known as tertiary winding. So S1 kVA is S2 plus S3. Now what is use of this third winding? So application, use of tertiary winding. Sorry. We have seen in star-star connection, which is preferred for high voltage, low capacity application, there is problem of unbalancing and harmonics, so that can be avoided by use of tertiary delta. I told you that the star-star cannot be used without tertiary delta, right? So that is tertiary winding. So in star-star connected transformers, it is used as stabilizing winding. To prevent unbalancing and harmonics. So how it prevent harmonics? The third winding permits third harmonic current to flow in it, right? So this tertiary winding permits third harmonic current to flow in it, and in this way it will not appear in output to flow in it. So therefore third harmonic voltage will not appear. Third harmonic voltage will not appear in output. Will not appear in output, right? So this is one application. Second, as we have three windings with different turns, that is different voltage, we can connect 3 power systems of different voltage levels. So it can be used to connect 3 power systems of different voltages, right? Along with this, as third winding is providing another voltage level, so this voltage level will be available in power plant for auxiliary system supply. So additional voltage level is available. So additional voltage level to supply auxiliary system in power plant, right? Along with this, it can be used to connect reactive power compensating equipment, to connect reactive power compensating equipments. And also we can use it for measurement. So for voltage measurement of HV testing transformer. Of HV testing transformers, right? So this is what the tertiary winding or 3 winding transformer, and what are the applications of it that we have seen. Let us see one important concept for solving various numericals which are there in syllabus. Per unit system, per unit written as PU, right? So what is per unit system? Per unit system is used during analysis of electrical machine and power system circuit. So during analysis of electrical machine, voltage, current, volt ampere and impedance are generally expressed in per units, or percentage of base values of these quantities, right? So what is importance of per unit? Per unit system helps us to do calculation very simple, right? What is per unit value? How it is written? Per unit is given as actual value of any quantity in a given unit divided by base value of same quantity in same unit, base value, right? So base value are generally rated value, So VA rating can be given as S base equal to V base into I base. I will write base in short as B. So I base can be written as S base by V base, right? What is impedance is Z base impedance will be V base by I base. I can write it as V base by, what is I base? I base can be kept from here. So I base is S base by V base. So it is what? V base square by S base. That is voltage into voltage divided by voltage into ampere, right? So Z base value is given by kVA. If I am writing, then it will be MVA. So kV square by MVA, right? Or we have written voltage square by base square, volt square by apparent power, that is volt ampere. Okay, so this is what base value of impedance, and I can write per unit impedance. As I know, it is actual value, so actual value will be given. So actual value, which is in ohm, divided by base value, and this is what base value is. What base value is V base square in divided by S base. So I can write here it is Z into S base by V base square, right? So per unit impedance can be written as Z actual value into VA rating by voltage square, or kVA rating. So this is what S base by V base whole square. So per unit impedance or per unit values system gives us simplicity in calculation. We will see some numericals also. Let us go for one numerical on parallel operation. We have seen parallel operation, and on parallel operation we know load shared by, if I have two transformers connected in parallel with equal voltage ratio, load shared by transformer 1 equal to load into impedance of second transformer divided by summation of impedance of both transformer. So this is what kVA, this is also kVA, load kVA, and this is kVA of transformer 1. And we also know kilowatt will be given by kVA into power factor, kVA into power factor, right? And kVA will be calculated by dividing kilowatt with power factor. So let us go for a numerical. And if I have two transformers, say S2 will be what? Total load SL minus S1, because total load is S1 plus S2, and it can also be given by, in terms of this formula, SL impedance of first transformer divided by impedance of both transformer, right? So in this way, if I have to solve one numerical, so see two single phase transformers with equal voltage ratio and have impedances of, so Z1 is given and Z2 is also given, right? 0.819 plus J 2.503 ohm and 0.8 plus J 2.31 ohm with respect to secondary. If they operate in parallel, how will the load of two 1000 kilowatt at 0.8 power factor, lagging will be shared. So load is SL is, it is 200 kilowatt, so I can find kVA 200 by 0.8 power factor. So 200 by 2000 by 0.8 is what? It is 2500, and it is at angle of minus, lagging power factor is 0.8, so it is what? Minus 36.87. Cos phi is 0.8, so phi will be, this is what? kVA, load kVA. So how the transformers will share load and their impedances are different. We know the impedance formula, and we know how load is shared by formula. We require S1 to calculate and S2 also, and for that Z1 and Z2 value is given. So let us find Z1 plus Z2, which will be used in solving it. So it is what? 0.819 plus 2.503 plus 0.8 plus 2.31 J. So it comes as 5.07078 at an angle of 71.4 ohm. Now load, that is in kVA, shared by first transformer, S1 will be SL, Z2 by Z1 plus Z2. So S1 is given as, SL is 2500 at an angle of minus 36.87. What is Z2? Z2 is this value, right? The Z2 is this one. So 0.8 plus J 2.31 divided by Z1 plus Z2 we calculated as 5.078 at an angle of 71.4. So if I do calculation, it will be 2500 at an angle of minus 36.87 into 0.8 plus 2.31 I, sorry, 2.31 I divided by 5.078 at an angle of 71.4. So it comes as 1203.5 at an angle of 37.37 minus 37.37. It is kVA, and if you want to write in kilowatt, so in kilowatt it will be what? 1203.5 cos of this angle. So it comes as cos 37.37. It comes as 956.46. So this power will be shared at this lagging power factors. Minus angle means lagging power factor. Cos 37.37 comes as 0.7947 lagging, right? So this is the power shared by first transformer, and power shared by second transformer as 2 can be written as total power minus power shared by S1. So SL minus S1. If I write SL in terms of kilowatt, it will be 2000 kilowatt at an angle of lagging power factor was 36.87 minus 956.46 at an angle of minus 37.37. So it comes as So it comes as 1043.6 kilowatt at 0.8047 lagging. I can write it in this form also, 2000 at an angle of minus 36.87 minus 956.46 at an angle of minus 37.37. It is what 1043.6 at an angle of minus 36.41, right? And in kilowatt we have calculated it. So that's all for this video. We will see few more numericals on parallel operation.